We will now learn a more systematic method for computing the GCD and LCM of a set of positive integers that uses the prime factorizations of the given integers. We will slightly modify the canonical representation of a positive integer in a way to ensure that we do not skip any primes and that each prime has a power. Let's look at an example. The canonical representation of 50 is 2 times 5 squared. Note that we skipped over the prime 3 and there is no exponent written for 2. We can easily give 2 an exponent by rewriting it as 2 to the 1. Since x to the 0 is equal to 1 for any non-zero x, this is by definition, we can write 1 equals 3 to the 0. Therefore, the prime factorization of 50 can be written as 2 to the 1 times 3 to the 0 times 5 to the 2. We will call this last prime factorization a complete prime factorization of 50. We will say that p0 to the a0 times p1 to the a1 times pn to the an is a complete prime factorization if p0, p1 through pn are the first n plus 1 primes and a0 through an are natural numbers. So p0 is equal to 2, p1 is equal to 3, p2 is equal to 5, p3 is equal to 7, p4 is equal to 11, and so on. Right? We're just listing the primes in order. Let's look at an example. The prime factorization of 364 in canonical form is 2 to the second times 7 times 13. However, this is not a complete prime factorization. A complete prime factorization of 364 is 2 to the second times 3 to the 0 times 5 to the 0 times 7 to the 1 times 11 to the 0 times 13 to the 1. This is not the only complete prime factorization of 364. Another complete prime factorization of 364 is 2 to the second times 3 to the 0 times 5 to the 0 times 7 to the 1 times 11 to the 0 times 13 to the 1 times 17 to the 0. Notice how we tacked on an extra prime at the end there to the 0 power. Given a complete prime factorization, p0 to the a0 through pn to the an of a positive integer, p0 to the a0 through pn to the an times pm plus 1 to the 0 is another complete prime factorization. In fact, for any natural number k, p0 to the a0 through pn to the an times pm plus 1 to the 0, pm plus 2 to the 0, through pm plus k to the 0 is also a complete prime factorization of that same positive integer. In words, we can include finitely many additional prime factors at the tail end of the original factorization, all with exponent 0. Just be careful not to skip any primes. Let's look at an example. 2 to the 0 times 3 to the 5 times 5 to the 0 times 7 to the 2 times 11 to the 0 times 13 to the 0 times 17 to the 2. And 2 to the 3 times 3 to the 1 times 5 to the 0 times 7 to the 0 times 11 to the 6 are complete prime factorizations. In many cases, it is useful to rewrite the second factorization as 2 to the 3 times 3 to the 1 times 5 to the 0 times 7 to the 0 times 11 to the 6 times 13 to the 0 times 17 to the 0. This is also a complete prime factorization. However, this one has all the same prime factors as the first number given. Complete prime factorizations give us an easy way to compute greatest common divisors and least common multiples of positive integers. Suppose that a equals p0 to the a0 through pn to the an, and b is equal to p0 to the b0 through pn to the bn are complete prime factorizations of a and b. Notice how we made sure that the number of prime factors matches up in A and B. In the last example, we saw how to do that if necessary. The GCD of A and B is equal to P0 to the minimum of A0 and B0 times P1 to the minimum of A1 and B1 times Pn to the minimum of AN and Bn. We take the smallest power. For LCM of AB, we do something similar, but we take the biggest power, P0 to the maximum of A0, B0, P1 to the maximum of A1, B1, Pn to the maximum of AN and Bn. Let's look at an example. Let A equal 2 times 5 squared times 7, and B equal 3 times 5 times 11 squared. We can rewrite A and B with the following complete prime factorizations. A equals 2 to the 1 times 3 to the 0 times 5 to the 2 times 7 to the 1 times 11 to the 0. And B equals 2 to the 0 times 3 to the 1 times 5 to the 1 times 7 to the 0 times 11 to the 2. From these factorizations, it is easy to compute GCD of AB and LCM of AB. GCD of AB is 2 to the 0 times 3 to the 0 times 5 to the 1 times 7 to the 0 times 11 to the 0, which is equal to 5. Notice how we took the lowest exponent each time for each prime. LCM of AB is equal to 2 to the 1 times 3 to the 1 times 5 to the 2 times 7 to the 1 times 11 to the 2, which is 127,050. This time we took the highest power of each prime. Let's also verify GCD LCM fact 1 for this example. Remember that GCD LCM fact 1 says that if A and B are positive integers, then the GCD of A and B times the LCM of A and B is equal to the product A times B. Well, A times B is equal to 2 times 5 squared times 7 times 3 times 5 times 11 squared, which is 635,250, which is equal to 5 times 127,050. Which is the GCD of AB times the LCM of AB, thus verifying the fact. Let's try an exercise. For each of the following, find the canonical form of GCD AB and the canonical form of LCM AB. Now's a good time to pause the video, try this exercise yourself, and then resume the video to check your answers with mine. Okay, the first one, A equals 2 cubed times 3 squared, and B equals 2 times 3 times 5 squared. We first rewrite these prime factorizations as complete prime factorizations. So we have A equals 2 to the 3rd times 3 squared times 5 to the 0, and B equals 2 to the 1 times 3 to the 1 times 5 squared. Okay, for the GCD, we take the lowest power of each prime. That's 2 to the 1 times 3 to the 1 times 5 to the 0. Which in canonical form is 2 times 3. And for the LCM, we take the highest power of each prime. So that's 2 to the 3rd times 3 to the 2nd times 5 to the 2nd. For number 2, we have A equals 2 to the 5th times 7 to the 3rd. B equals 3 to the 2nd times 5 to the 3rd. We, once again, first rewrite these factorizations as complete prime factorizations. So we have A equals 2 to the 5th times 3 to the 0 times 5 to the 0 times 7 to the 3rd. And B equals 2 to the 0 times 3 to the 2nd times 5 to the 3rd times 7 to the 0. Again, for the GCD, we take the lowest power of each prime. That's 2 to the 0 times 3 to the 0 times 5 to the 0 times 7 to the 0, which is just 1. For the LCM, we take the highest power of each prime. That's 2 to the 5th times 3 to the 2nd times 5 to the 3rd times 7 to the 3rd. Okay, for number 3, we have A equals 3,872, B equals 16,731. We first write complete prime factorizations. You may want to make factor trees for these if you don't see where I got these complete prime factorizations from. A is 2 to the 5th times 3 to the 0 times 5 to the 0 times 7 to the 0 times 11 squared times 13 to the 0. B is 2 to the 0 times 3 squared times 5 to the 0 times 7 to the 0 times 11 to the 1 times 13 to the 2. Again, for the GCD, we take the lowest power of each prime, 2 to the 0, 3 to the 0, 5 to the 0, 7 to the 0, 11 to the 1, 13 to the 0, which is just 11. And for the LCM, we take the highest power of each prime, 2 to the 5th times 3 squared times 5 to the 0 times 7 to the 0 times 11 squared times 13 squared. That simplifies to 2 to the 5th times 3 squared times 11 squared times 13 squared. Okay, for the last one, we have A equals 12,274 and B equals 122,825. Again, after making some factor trees, we can write down complete prime factorizations for these. A is 2 to the 1, 3 to the 0, 5 to the 0, 7 to the 0, 11 to the 0, 13 to the 0, 17 to the 1, 19 squared. B is 2 to the 0, 3 to the 0, 5 squared, 7 to the 0, 11 to the 0, 13 to the 0, 17 cubed, 19 to the 0. Again, for the GCD, we take the lowest power of each prime, which simplifies to 17. And for the LCM, we take the highest power of each prime, which simplifies to 2 times 5 squared times 17 cubed times 19 squared. Let A and B be integers. A linear combination of A and B is an expression of the form MA plus NB with M and N integers. We call the integers M and N weights. Let's look at an example. 5 times 10 minus 2 times 15 is equal to 50 minus 30, which is 20. So 20 is a linear combination of 10 and 15. When we write 20 as 5 times 10 minus 2 times 15, the weights are 5 and negative 2. This is not the only way to write 20 as a linear combination of 10 and 15. Another way, negative 1 times 10 plus 2 times 15, which is negative 10 plus 30 is 20. When we write 20 as negative 1 times 10 plus 2 times 15, the weights are negative 1 and 2. As another example, any number that is a multiple of either 10 or 15 is a linear combination of 10 and 15 because we can allow weights to be 0. For example, 80 is a linear combination of 10 and 15 because 80 is equal to 8 times 10 plus 0 times 15. Also, 45 is a linear combination of 10 and 15 because 45 is equal to 0 times 10 plus 3 times 15. It turns out that for any integers A and B, the GCD of A and B can always be written as a linear combination of A and B. For example, the GCD of 10 and 15 is 5, and we have 5 equal to negative 1 times 10 plus 1 times 15. So if A and B are relatively prime, then 1 can be written as a linear combination of A and B. For example, 4 and 15 are relatively prime, and we have 1 equals 4 times 4 minus 1 times 15. Linear combination fact 1. Let A and B be integers, at least one of which is not 0. Then the GCD of A and B is the least positive integer k, such that there exist integers m and n with k equal to ma plus nb. Note, linear combination fact 1 says two things. One, that GCD of A and B can be written as a linear combination of A and B. And two, a positive integer smaller than GCD AB cannot be written as a linear combination of A and B. Let's try another exercise. Express K as a linear combination of 12 and 18, or explain why it is not possible. Go ahead and pause the video now. Try this exercise yourself, and then resume the video to check your answers with mine. K equals 12. Well, 12 is 1 times 12 plus 0 times 18. K equals 18. 18 is 0 times 12 plus 1 times 18. K equals 6. 6 equals 2 times 12 minus 1 times 18. K equals 36. 36 is 12 times 12 minus 6 times 18. K equals 3. This is not possible because the GCD of 12 and 18 is 6, and 3 is less than 6.